So what we're going to look at, have to remember, is limits in essence are algebra problems with like a tiny little bit of calculus sprinkled on top. The notation is what intimidates everybody. Everyone's always like, I hate limits, they're so hard. They really aren't. You just have to get used to how stuff is written. That's all. It's like learning another language and you're learning the symbols. Okay. So what we're going to do is fill out this table for this function. If I get rid of this limit, it's an algebra 2 problem. You all passed algebra 2, okay? So this is algebra, this is calculus. Do you see what I'm saying? Like, it's just some notation. I'm going to share my screen. I'm going to type that in. And while I'm typing, it's your job to make sure I don't do anything wrong, because if I do, then the whole thing is not going to be correct. I get that it's not fun to watch your teacher stuff, but I want us to stay together as a group here. Do you see how I got that typed in? And I hit this little gear button, hit table. If you didn't know, Cosmos will give you a table of values for the function. Now, what does it say is going on at -2? Because that's kind of the whole point of like what we're doing here. Undefined. So on your table at -2, you can go ahead and put undefined. That means there's two options of what's happening there. What are the two things that could be happening if you get an undefined? Yeah, a whole or an asymptote, one or the other, okay? So let me go back. I can't have my paper and my calculator up at the same time, so you're going to have to kind of listen to me, write this down. I'm going to go to the next box down in the table. We're going to type in that first value, -2.5. So in your table, the first number is -1.4, and I'm just going to type them in one at a time. You see how I did that there? Desmos is really cool that it'll do all this for. Oops, I accidentally put a slash. Okay, so then the next one, we're kind of like, use microscopes in science class. Do you still do that? Is that even a thing? Or like, yeah, or like, you know what a microscope is? You know how you can like zoom in on something? That's what we're doing. We're taking this graph and we're zooming in on this one point. So we're going to try and get like closer and closer to it. -2.1. I know that's kind of small. I'll read it to you. -1.068. So put that in the next box of your table. -1.068. And then the next one is -2.01. Again, do you see how we're getting closer and closer and closer and closer? Okay, so that is -1.006. Now we're going to go on the other side. So on the other side, I'm going to put -1.99. So it is -0.993. And then the next, now we're getting further away. So -463. Oh, -1.9. I am so sorry. See, that's your job whenever I'm typing, is make sure I don't mistype or it's wrong. Here we go. -0.935. Thank you. Good eyes. I would have caught that because the decimals wouldn't make any sense when I go back to my paper. And then -1.5. So -714. The whole point of this is, I want you guys to look what is happening from both sides as you get closer and closer to -2. Do you see how this is going to be -0.9? Like if I zoomed in further, -0.9999999, and this would be -1.00000 something. What are they both getting super, super close to? -1 is the answer to the question. Okay, you have done this before. If I cover up this limit notation, what does it feel like you need to do? It's rational. And what does it feel like you need to do to it? Factor. Good. If you factor the numerator and factor the denominator, let's see what happens. Numerator would be x and x. How else is that going to split? 2 + 1. Yeah, 2 and 1, it will be +2 -1. All right, and then in the denominator, sorry, I can't talk. 10 is going to split, 2 and 5, 5 and 2, whatever order you want to write it in. And then to get 7 in the middle, they're both plus. So what happens? This is like the whole point of the thing. So that means it's a whole. And we did this earlier this year as well. If you want to find the whole, it's going to be -2. And then how do you get the something where the whole is? You take -2, plug it back in. -2 - 1. -3. -2 + 5 is 3. And what does this equal? A limit is this. If you zoom in on a point, it is what you are getting closer and closer and closer to. You have to hear me on this because this is the crux of the whole thing. It doesn't matter if it's actually there or not. It can be a whole. It is the behavior of the graph. And this is the analogy I always use. Have you ever been walking up the stairs and you're not paying attention and you get to the top of the staircase and you take another step anyway, even though it's not there, and then you trip and fall and drop all your things and everyone laughs at you, okay? It doesn't matter that the step's not there. If it was there, your foot would have landed exactly on it because that's how a limit works. It's just behavior of what you're getting closer and closer to, okay? So we're going to go over a little bit of vocabulary, and then there's no work to these questions. You kind of just answer them. You look at the picture and answer it. So it is like a pattern, but specifically at a certain point. Right? In order for a limit to exist, the same value is approached from both sides. So both sides have to match. Otherwise, the limit does not exist. And we've all seen Mean Girls, right? You know how at the end, she's like, the limit does not exist. If you watch that movie and look behind her, there is a picture of a graph where the two sides are going completely opposite directions from each other. And if you understand calculus at all, you would be like, duh, the limit does not exist. The funny scene in the movie. Yep. So same value is approached from both sides. Second thing, there's three things here. The graph does not increase or decrease without bound. Without bound means forever. Now there's a caveat to this. You can get an answer of positive infinity or negative infinity as long as it's only from one side or the other. Because, for example, when you have an imagination, can you imagine this with me? If you have an asymptote, even if both sides are going up, you can't say the answer is positive infinity because will they ever touch or meet up? No. So you would have to say does not exist. Now, if it's just from one side, you can say that that's the answer. All right. And then the third thing is the graph does not do what's called oscillating. The graph does not oscillate. And I will show you a picture of what an oscillating graph, it matters if you spell that right or not, I'm not concerned about that. Let me show you an example of what an oscillating graph is. Just look at this because it's kind of cool. It's interesting. If I type sine 1 over x, see that there? Now, if I try to do the limit at 0, I'm just going to zoom in like a microscope on 0. Do you see what's happening here? So what's happening is the graph is just like this at 0. There's no overall behavior. You can't say that it's approaching a certain number because it's just going crazy. Okay. That's what oscillating is. Like the graph lost its mind and just freaked out. And so you can't get an answer. Right, now these, there is no work. You are simply going to write an answer. I don't have a better explanation than, hey, look. So you're going to have to watch me point to it. Okay. We're just going to use this graph that's here. So this says limit as x approaches -1. Watch me point to it. Here's -1. What value is getting approached from both sides? Well, I heard somebody say it. 0. There you go. That's the answer. Don't overthink it. This one says limit as x approaches 1. Watch me point to it. I don't care that there's a hole there. In fact, the point is actually up there. That's like, nah, I tricked you. Point's up here now. I don't care about any of that. What value is being approached from both sides if I zoom in on that? I don't care that it's not there. -1 is your answer. Again, it's like falling up the steps. It doesn't matter that it's not there. If it was there, both sides, like if I zoom in on that, both sides are getting closer and closer to that. It's the same situation that I used as the lead into the whole thing up there, right? Now this says -6, and there's a little plus sign. That means from the right or the positive side. So we're going to look at -6, which is right here. We're only going to look at the left side. So you actually can get an answer. Where is this arrow going? -infinity. So, oh, sorry, it was supposed to be from the right. Still, the answer is going to be -infinity. Now, if you do -6 from the left, again, that's going to be -infinity. But look at this one. See how it's just -6 and there's not a plus or minus? You can't get an answer because these two arrows are never going to touch. They won't ever meet. There's an asymptote in between. So we have to say does not exist. Don't say undefined. That is a subtly different thing. So does not exist. If there's an asymptote, you can only get an answer if it's from one side or the other. If it's both, because the asymptote is separating this, the two sides will never be able to like come together. So there's no like overall behavior. All right, this is -2 from the left. So look there's a jump here. Watch me point to this. -2, we're going from the left. I don't care that there's nothing there. If you approach from the left, what value is being approached? -1, good job. All right, -2 from the right. Again, watch me point to it. This time we're coming from the right. -2 from the right. Can we just call that 2? Yeah. The graph is off a little bit, but do you get what I'm saying? Like, just pretend. We'll use our imagination. We'll just say it's 2. And then what is limit as x approaches -2 overall? There's not a left or a right. Well, this side goes down here and this side goes up here. So yeah, it does not exist. Both sides have to approach the same value. Like a microscope, if you zoomed in on it, there's no behavior. Now, you've been doing these for a long time. You started this in Algebra 2. This is just end behavior, and I've gotten you used to this notation. Limit as x goes to -infinity. Where do we level off on the left side? 0. Will it ever touch 0? No, it's behavior. The reason I've said that all year long is because that's a limit. That's what I'm trying to get you, used to. Limit as x goes to +infinity. So that's this side. That levels off at -2. Good job. All right, this is 4 from the left. So I will point to it. Here's 4. We're going from the left, -infinity. Good job. And then 4 from the right, +infinity. And then 4 overall does not exist because there's an asymptote. And also 1 goes up and 1 goes down. So very obviously, like on Mean Girls, it's not going to exist. All right, so -5 from the left. So where's -5? -5 is right here. If we approach from the left, or it kind of doesn't really matter that it's from the left in that case, we are approaching. Yeah, can we say -2? I mean, it's hard to tell kind of there, but we'll say -2. And then limit as x goes to 5. I don't care that there's nothing there. It's like falling up the steps. From both sides, what's being approached? Are you going to answer the question or ask me something? Well, I'd like for you to not change the subject while I'm asking something, so hold on just a second. 0 is the answer to that. Okay, go ahead. No, you need to zoom in just on -5. So we're zooming in like literally just right there. Do you see what I'm saying? The asymptote isn't even a part of it because the asymptote is not at -5. The asymptote's at -6. Which, if you think about it this way, -6 is actually really far away from -5. There's an infinite number of values in between them. Don't think about it too hard. We're not actually capable of understanding infinity. You have to like handle it gently. Like think about it, but like lightly. Yeah. Yeah. I mean, yes, and some infinities are larger than other infinities if you've read The Fault in Our Stars. Has anyone ever read that book? Or seen the movie? Yeah. Some infinities are larger than other infinities, which is true. So interesting. Now, this is not calculus. This is not calculus. This is just where's the point? Like, where's the actual value? Now, I am going to have to kind of move the paper up and down to do this, unfortunately. But f of -2. So you have to look at -2. Where is the actual functional value, like the filled in point? And we'll call that 2. Okay. All right. F of -6. There's an asymptote there, so does not exist. How about f of 1? That's the tricky one. That's like, nah, I tricked you. But 4, good job. F of 5. Yep, there's a hole and we don't have a point somewhere else, so there isn't one. What's that? Holes do matter. Yeah, if you're looking at for an actual value, this is not calculus. This is just regular old algebra. This is just, is there a point there? A limit is behavior. That's like falling up the steps. All right, how about at 4? Yep, there's an asymptote. How about at 0? -1, good job. And then -1 is 0. Ah. All right, so the other thing that we're going to talk about is continuity. So in order for a function to be continuous, and we've done continuity, I just gave you kind of like the pre-calculus definition. If you can trace without lifting your pencil off the paper. All right, for calculus, you're going to get like the sort of more grown-up definition. All right, so to be continuous at a value c, when you do an actual problem, c will be a number like 3 or 7 or -2. Okay, but like for this, it's going to say c. So in order for it to, for your function to be continuous, f of c exists. And that should make sense. There has to be a point there. If there's a hole, obviously it's not continuous. Oops. Or an asymptote, if there's an asymptote, it's not continuous. All right, the limit as x approaches c for the function exists. So there has to be a point and there has to be a limit. Both sides have to come to the same place. If there's a jump, obviously it's going to be broken. That would be discontinuous. And then the third rule, and I kind of ran out of room to write it down here, so I'm going to come over here, is just that those two things have to equal each other. Everyone always gets confused with writing this one out. Like those two go okay, and then the third one's weird. I don't understand why. Just instead of writing exist, just take these two things and slap an equal sign in between them. You're saying that these two things equal each other. The point equals the limit. So I'm going to show you how we could break those rules. So there's the rules. Now we're going to break them. You know, learn the rules and then break a few. All right. So there's two ways that your point would not exist. That would be a hole or an asymptote. So if your point is missing, there is not something there. If the limit doesn't exist, that would look like this, which would be a jump. So see, we have a point, but there's no limit. If I zoom in, the behavior from both sides doesn't match up, and so it's broken, so discontinuous. And then the third rule is you have a point and you have a limit, but they don't equal each other. This is the situation where it's like, nah, I tricked you. I've stole the point, now it's over here. So you have a point and you have a limit, but they don't equal each other. You took the point out. Do you remember removable discontinuities? Non-removable, that's what we're talking about here. So what we're going to do, and that's the exact same graph that was printed on the other side of the paper. It's just reprinted here so you don't have to keep flipping back and forth. We're going to say yes or no if the graph is continuous or discontinuous. And if it's a no, then we have to give a reason. Like basically you say which rule got broken, okay? So let's look at 4. What do you think, yes or no? Here's 4. Continuous or not? Not. Okay, yeah, like the yes or no is going to be easy. That's going to be on instinct. Now you want to go through the rules in order because they kind of go easiest to most difficult. Is there a point at 4? Do you have an actual value at 4? No. So the easiest way to put it is f of 4 does not exist. There is not a point. It is missing, discontinuous. All right, how about -2? Do you think yes or no? At -2, no, okay? There is a point, but then there's a hole down here and it's broken, so we don't have a limit. The same value from both sides is not like meeting up. Like if I were to zoom in, I don't get the same value from both sides. So the limit does not exist. Limit is x goes to -2 of that function dna. That's how we put that. Again, it's the notation that gets everybody. Everyone could say yes or no. That's the easy part. And then how to write it is what's difficult. All right, what do you think about 3? 3 is right here. Yes, you can trace through that without lifting your pencil. So that's a yes. How about -6? No. Is there a point at -6? No. So you just say f of -6 does not exist. There's not a point there, so it can't be continuous. How about 5? Correct. It is not. And what's your reason why? What's going on at 5? Yeah, there's a hole, so it would be f of 5 does not exist. You can't say there is a hole. You have to use correct notation in calculus. All right, how about 1? What do you think at 1? That is no. Now there is a point and there is a limit. Both sides come to the same place, but they don't equal each other. So here's how we write that. F of 1, that's the point, doesn't equal, that's like your no parking sign, the limit as x goes to 1 for the function. So you have a point and you have a limit, but they don't equal each other. And again, that's like, haha, I tricked you, the point is over here now. Like I stole it. These are intervals. So from 8 to infinity. So we're looking from 8 onwards this way. What do you think? Yes, that's continuous. You can trace it without lifting your pencil off the paper. This looks like an ordered pair, but it's not. It's from -5 to -2. But what do the parentheses mean? Yeah, you don't need to include those, doesn't equal those. So from -5, which is right here, up to -2, but I don't need to include that one. So what do you think? Continuous? Yeah, we're continuous there. So yes, which is great because then you don't have to do anything else. All right, from 5 to 7, but you do need to include them. So what do you think? From 5 to 7, that's a no, and it's because we're missing the points at 5. So we would say no, f of 5 does not exist. And then last one, from -1 to 1, that's this portion right here. But there are brackets, so it would be no. Oops. And the reason why is the exact same thing that we wrote here. So you can just copy that over. The points and the limit do not equal each other. There is a point and there is a limit. They just don't equal each other. Now, if you want to be super particular, which often in calculus you do have to be, if you're on the interval -1 to, no, I'm going to add something to that. Hold on a second. If you're on the interval -1 to 1, you can only approach 1 from which side? From the left. So you technically have to put a little negative in there to show that it's from the left. Bless you. Now I think this next page, oh no, I put that on the back. This back page is just extra practice if you're interested in it. I'm going to leave that for you guys. I can post the answers. We've done this already this year. It was way back when we did piecewise function. Oh, do you remember this? All right. If you want the function to be continuous, you have to set the two pieces equal. Good. So you're going to take x squared minus 2 equals x minus p. Set them equal. And then at which particular point do we want it to be continuous? Good. So you're going to plug -1 in everywhere that there is an x. And then just solve. Just do algebra to solve it. So what is -1 squared? That's 1. And then 1 minus 2 is -1. Gosh, I wish I could write without breaking this. Equals -1 minus p. So this is kind of interesting. If you add over the 1, what do you end up with? Yeah, 0 equals -p, but I mean, you can't negative a 0, so just end up with 0. Everyone try one more. We want the function to be continuous, so you're just going to take the two parts and set them equal. Like literally just write it and slap an equal sign in between. That's all that you're doing. You want them to meet up. Do you really remember this from before? This was so long ago. I'm impressed that you did. Okay, cool. And then what number are we going to plug in for x? 4. Good. So p squared minus 2p plus 4 equals, I'm going to guide you through doing this in your head so we can do a little bit less writing. If we plug in 4, what is 4 squared? Is 16 plus 3, 19. Now this is welcome back to Algebra 2. Make your Algebra 2 teacher proud. But what do I call this step? Evacuate, evacuate. Get everybody over so it all equals 0. We're going to minus the 19. What would that be? -15. And so we're going to get 2 answers when we factor this. So how is 15 going to split? 5 times 3. And you want a -2 in the middle? Yep, good. And then so your answers are p equals 5, p equals -3. Here's what I'm going to do. The back page is just more practice of the same. I'm going to fill it out real quick, take a picture of it, and I'll post that if you're interested and you want to see it for extra practice. But all you have to do is your delta math. When you finish that, you can just find something to work on quietly. We're kind of done. Congratulations. That was the last lesson of the year.